In this unit, we're going to be examining alkene reactions, which are commonly known as addition reactions. These are going to work in the opposite way of the elimination reactions. In the case of the alkene reaction we are starting with, you guessed it, an alkene. We have a double bond somewhere in our molecule. It doesn't have to be in the middle, it could be on the end. And we are going to add something to it that is going to break that double bond and instead form a functional group. Now, in the case of hydrochloric acid, we got a chlorine over here and a new hydrogen over here, fully saturating this carbon. But those normally get hidden, so we don't need to draw it here. We could also have worked with water, giving us an alcohol, or we could use pure chlorine, Cl2, and that would give us two functional groups. So we can have a lot of different additions when we're working with alkenes, and there are a lot of different mechanisms that these reactions can go over. We're going to cover two specific reactions, and in the process, we're going to learn a little bit more about how these alkenes are set up. In order to examine these mechanisms, though, there's some key vocabulary that we need to get straight first. The first two keywords we need to look at are Reggio and stereo. These are going to be referring to isomerism. Reggio is going to be specifically the constitutional isomerism. So let's write that. And when we talk about Reggio products, we're going to be talking about the products of a reaction. Reggio is going to come into play when we have something like this alkene with hydrochloric acid. We just saw that this hydrochloric acid plays a double bond, but in our products, we find the Cl on this side. So we're going to use Reggio as a keyword when we're talking about where is the physical placement of the functional groups that get added. Stereo is going to refer to stereoisomerism. Go figure. And when we talk about stereoisomerism, we could look at something like this cycloalkene that has a methyl group right next to that double bond. Our chlorines are actually going to attach to this in a very specific way according to the stereochemistry. We're actually going to have one of our chlorines. So when we have a reaction like this, we're actually going to see a specific stereochemistry where our chlorines are on the opposite sides of each other on this molecule. We can either have the right one going forward and the left one going backwards, or vice versa, but not both. We can't have them both going forward or both going backwards. It just doesn't come out that way. So there is a level of stereochemistry that gets retained and has a seeable, visible pattern. And we need that word. We need these Reggio and stereo words to help us describe that. The next two words that we're going to look at are specific and selective. And these are going to pair with Reggio and stereo to give us really accurate descriptions of the products of these reactions. Specific is going to refer to something always occurring in that exact way. Selective is going to refer to something being more commonly one way or another. So what's an example of this? Well, when we were looking at the SN2 mechanism, remember, our stereochemistry would always get flipped, like an umbrella being flipped inside out by the wind. So we had stereo-specific products. So it was always one stereoisomer. So we can have a lot of things occurring in a very specific way. We're going to see that we have some Reggio specificity where we wouldn't quite expect to have it. And that's going to help us understand the mechanisms at work. We're going to see stereo selectivity and stereo specificity where we normally wouldn't expect it. So these are going to be terms that we're going to be able to use to describe our products that'll help us investigate mechanisms. So within stereospecificity, there are another two key words that we're going to be using that are going to really inform our mechanisms. These two words are syn and anti. What these refer to is the placement of the forward and backward stereochemistry. In syn products, everything is going to be facing the same way. So if I've got chlorine being added to an alkene, a cycloalkene, cyclohexene, and both come forward or both go backwards, this would be syn products. If I have them going one way or the other, it doesn't matter which way it is, as long as they're going opposite ways, it would be the anti-product. And since we are always going to be working across a double bond here, we're going to see this come up across two carbons. So our products are functional groups that get put in, whether that be a chlorine or often another hydrogen. We're going to see sometimes they'll go forward, sometimes they'll go backwards, sometimes they'll flip-flop. And we're going to need to be able to use that to investigate our mechanisms. So you'll see these vocabulary terms used a lot. And there's one more that can be pretty confusing. So let's take a look at that. All right, this last key word is going to be Markovnikov. And it's a reference to Markovnikov's rule, which was a rule that was discovered by a guy named Markovnikov. I believe he was Russian. Markovnikov sounds very Russian. But what you'll hear very often when we're working with alkene reactions is Markovnikov addition or Markovnikov products. What this means is their products are going to follow a very specific rule. And that rule is basically a rule of thumb that the hydrogen so this hydrogen and this chlorine are going to be attacking or being attached across this double bond. So the hydrogen is going to bond to whichever carbon has more hydrogens. Likewise, the acid is going to bond to the carbon that has more alkyl substituents. So we can say the acid is going to bond to the carbon that is attached to more carbons. Okay, so we can see in this reaction, that's a great example. My hydrogen and chlorine are both going to be bonding to one of these carbons. So let's go ahead and name these. Let's call this the alpha carbon. Let's call this guy the beta carbon. Fantastic. So, would the hydrogen bond to the alpha carbon or the beta carbon? Which one? The red one or the blue one? I could have just called them red and blue. The hydrogen is going to bond to the carbon that has more hydrogens. Well, this carbon is attached to this carbon over here with 1, 2 bonds. Then it's attached to a carbon down here. And so it's attached to one hidden hydrogen. This carbon over here is attached to the other carbon by 1, 2 bonds. Then it's attached down here to another carbon and up here to another carbon. So this guy, beta carbon, has 2 alkyl substituents. Well, technically 3. This one only has, well, 1 alkyl, 1 alkene, and 1 hydrogen. So this one has more hydrogens. This one doesn't have any. So we could see in predicting the outcome of this reaction, once we look at these mechanisms, it'll be a little more apparent, but we would see that our chlorine would attach here and our hydrogen would attach here. That's what Markovnikov means. So as we investigate these mechanisms, the two that we're going to look at, we're going to be able to say, does this mechanism have Markovnikov products or not? Is it stereoselective? Is it Reggio specific? So Markovnikov would be an example of being Reggio specific. This is going to be important to remember and kind of get a hang of because when you take organic chemistry in college, you're going to be looking at a lot more than 2 alkene reaction mechanisms.